And so you're doing a PhD with CSIRO, CSIRO, which is Australia's premier scientific research organization. And I know that there are lots of things that you can't tell us about what you do in your secret space junk projects. But maybe there are some things you can tell us about this PhD work that you're doing.
Yeah. Well, so CSIRO is like the national laboratories kind of mixed with the NRAO kind of equivalent in Australia. So they own most of the radio telescopes, and they've let me use some of those for my PhD. So the topic is kind of like most people nowadays have heard of the space debris crisis. So they've seen the movie Gravity and they've heard of Kessler syndrome. So they know that there's junk in space. You know, we've been putting junk up there since the 50s. And we
The
don't.
bit in Gravity where space junk hits whatever the space station that we're in or whatever, that is one of the most frightening parts in the movie.
Yeah. Absolutely. And it brought a lot of attention to it, actually. It's been really quite effective as outreach because everyone's like, oh, yes, like the movie, that Sandra Bullock movie. Now I know. So it's actually been great. But
yeah, it's easy for me. Like it was very easy for me to remember about space junk because I always think about that time that I pooped my pants in theater. That I had to. I'm like, oh yeah, that time that I pooped in my pants. Space junk. I didn't actually poop in my pants, I promise. But that was. I mean, Gravity was a stunningly. I bet it happened to someone out there. It was stunningly intense film.
Visceral. Yes.
Indeed.
Well, yeah. So, like, we know that we've put stuff up there in orbit. And for a long time, we just went, oh, well, space is big. They won't go near each other. It won't matter. And we ended up having this Don Kessler who was doing simulations about how asteroid fields form based on these cascade collisions. So, like, one asteroid will hit another asteroid and it'll break parts off and they'll hit other asteroids. And that's how you end up with, like, given a certain amount of time, eventually the size of asteroids in an asteroid belt will largely homogenize because they will have all ground each other down. And anything that's much larger than something else would end up being broken apart because of the speeds involved, etc., etc. And he started going, hey, what about these things that we keep putting in space that's nearer to us? Satellites, what's up with those? And he figured out that if you look at it in the same way, that because satellites, yes, there are relatively few of them in a very big space, but they end up in similar kinds of orbits. And particularly now when we look at what's fit for purpose, we want things to be in particular orbits, then they actually do get close enough that they can hit each other. And there are cases where they have spectacularly hit each other because you've got to think about how something in low Earth orbit is moving like 10 times the speed of a bullet. So something that's this like millimeters big can take out a much, much larger object. So on average, if one piece of junk hits something else and it breaks apart, it will create about 10 other pieces that are capable of doing the same mass destruction as the original, which means you do get this cascade effect. That if something hits something the wrong way, it could flow on and that could hit something and that could hit something, and we could have a ablation cascade in orbit, which will make orbit unusable. We won't be able to have satellites anymore. We won't get space exploration. We'll just be surrounded in a fast-moving field of shards. It's rather important to keep an eye on.
That kind of seems like what we deserve at this point. I mean, we don't worry about enough things. We just keep like creating carbon dioxide in the atmosphere and producing more styrofoam, and it just seems like that's the future that that we've earned.
A very human thing.
Yeah, we're just going to fill space with junk, make it completely unusable. And some people, some states are helping us along by every once in a while firing a rocket at a satellite and making sure that they can do that.
Like Russia did that in November. And we've had a few other times where, like, I think China and India have also done anti-satellite weapons tests.
Those are the countries I was thinking of. Yeah.
And every time the US goes, like, my goodness, cannot believe they've done this. There should be laws about this when the US has done more of this than anyone else. Like, call up Project Starfish when they were nuking the atmosphere just to see if they could. They've been doing it for decades. They had that... There's this really awesome photograph of one of the first anti-satellite missile tests that was done by the US, which wasn't a like truck-based, land-based missile, like a little rocket, like you would think of. Like the Chinese ASAT test was like a truck-mounted rocket. The first one that the US did was actually on a fighter plane. They got someone to fly Mach 1 straight up and fire at a satellite in orbit, and he hit it.
Wow.
Crazy. And someone got a photo of it. It's awesome. But yeah, no one's ever attacked another country's satellites, but they attack their own just to show they can, just so no one messes with them.
Back off. So, okay. So we kind of understand the space junk problem really well now. Yes. And so does what you do in your PhD have anything to do with machine learning, or what are you up to?
Well, it was supposed to, but actually, so it's in this domain called space domain awareness or space situational awareness, or is sometimes called space traffic management or space surveillance. There's lots of different terms because it's rather new, and that's how fields work. When they're brand new, everyone makes their own names. And so similar to like we have air traffic control for planes, which has to keep track of where all the planes are, where they're going, what their objectives are, and then try to route them so that they all get to meet their objectives without running into each other. We have to do a similar thing for satellites. So because we don't have any robust, scalable, really well developed to maturity solutions for going up there and grabbing debris and bringing it back down, which even if we could only do that for like low Earth orbit. We've got things out at Lagrange points that we're just never ever going to be able to get them. So if we can't remove debris, the best thing we can do is know where it is and try to move things out of the way if they're about to hit, which means that all over the world, we have sensors that look at the sky and try to keep track of the 5,000 active satellites, the 35,000 large debris objects, down to like the 130 million we think maybe of tiny fragments of debris that are out there. But the worst thing is that orbits aren't stable. Like you'd think you would put something in an orbit and it will stay there, but it turns out that's not the case because the sun does stuff which creates pressure around Earth, and we've got these like charged particle belts that like push things outwards. And also like when something's in low Earth orbit, they drag along the top of the atmosphere, which means they slowly skew. And it means that actually we need to re-identify and replot the trajectory of every object basically every 24 hours, or it will be completely wrong. And also at this distance, if we can't figure out where it's going to be, we probably won't even be able to find it again. So
oh my God.
It's a constant chase, and we're trying to get better and better at predicting their trajectories given what we know about the physical forces at work, but they're so complicated and we can't do it fast enough. We don't have enough radars.
I had no idea.
To pick everything. So actually my work slots into the more instrumental side of things, where in astronomy you have the people who are instrumentalists, who are the ones who work with the sensors, the instruments. And so assuming that one radar to look at space can cost $1 billion and take 5 years to build, and we need them all over the world and enough of them to keep up with the growing rate of satellites in space, we went, oh crap, we obviously can't build them fast enough. What can we use? Well, we have radio telescopes. But astronomical radio telescopes are made to look at deep, deep space. So if you get an array of them and all of the algorithms they use assume that there is basically an angular difference of 0 because something is so far away. It's like if you look with your two eyes at something really, really far away, your two eyes are basically seeing the same thing. But if you look at something that's here, all of a sudden what your different eyes are seeing looks quite different. So I started out thinking that I would be working in machine learning to try and get better at like predicting those orbits and also identifying what object we were seeing, because if we're not using optical, we're using radios, we have to identify it based on transmissions alone. But now I've ended up looking at how we can adapt radio telescopes that were designed for astronomy, be able to see things right at the end of their noses, which means reframing the algorithms they use to like account for Earth's rotation while they're observing and account for Doppler shift and all these complicated electromagnetic things, some of which are beyond my grasp. It's quite hard.
Well, it sounds fascinating. And so you've ended up not so much doing machine learning in your PhD like you anticipated, but instead high performance computing. So taking advantage of your very strong programming background.
I love GPU programming. So it's the fun little package. If you haven't ever done GPU programming, the easiest way to explain it is that you have to pass everything you want the GPU to do in one neat little package. You have to say, here is the like million data points that we want you to operate on, and here is the operation that we want you to perform, and here is the hardware context that you're going to operate in, and here is where you put your results, and you have to like pass these little chunks. And I guess it's slightly closer to the metal than typical CPU programming. And yeah, it's really fun, and the kinds of speed up you can get is crazy.
So is that like CUDA that you end up using a lot of, or something else? Yeah, CUDA.
I mean, you can do like OpenCLC, but everyone has basically decided on NVIDIA as the default now that you've got the awesome like 3090s.